Design a URL shortener. Build me something like bit.ly or TinyURL. If you do enough system design interviews, this is the question you will hear more than any other. And there is a reason it is the classic opener. In one small, friendly-sounding problem, it quietly tests about 7 different skills at once. Can you gather requirements before you code? Can you estimate scale with rough numbers? Can you design a clean API? Pick a data model. Solve the one genuinely tricky part, generating short unique codes. Add caching. And scale the whole thing when traffic grows. Most candidates jump straight to a database table and start drawing boxes. The strong ones follow a framework. So in the next few minutes I am going to walk the entire question, start to finish, the way a senior candidate would answer it out loud, 8 clean steps you can reuse on almost any design question. Step 1, and never skip this, clarify the requirements before you design anything. Jumping to a solution is the fastest way to fail this round. Take 60 seconds to scope the problem out loud. Split it into 2 lists. Functional requirements, what the system does. And non-functional requirements, how it has to behave. Functionally, there are really just 2 must-haves. 1. Given a long URL, create a short one. 2. Given that short URL, redirect the user to the original long one. That is the core. Then there are nice-to-haves you should name and park, custom aliases, so a user can pick their own code, link expiration, and click analytics. Non-functionally, this is where you sound senior. The system needs high availability. If the shortener is down, every link everywhere breaks. Redirects must be low latency, because a human is waiting on a page load. And crucially, it is extremely read-heavy, people click short links far more than they create them. A common assumption is a read-to-write ratio on the order of 100 to 1. Say that number out loud, it drives the entire design. Step 2. A quick back-of-the-envelope estimate. The interviewer does not want a precise figure, they want to see that you can reason about scale and pick round numbers you can do in your head. So let us assume a scale. Say the system takes on roughly 100 million new URLs per month. Turn that into a write rate. A month is about 2.5 million seconds. 100 million divided by 2.5 million is about 40. So we are writing roughly 40 new links per second. That is small. Now reads. We said reads are about 100 times writes, so on the order of 4,000 redirects per second. That gap, 40 writes versus 4,000 reads, is the single most important number in the whole design. It screams, optimize for reads, and put a cache in front. Now storage. Keep 100 million a month, times 12 months, times 5 years, that is around 6 billion links. Give each stored record maybe 500 bytes for the code, the long URL, and some metadata. 6 billion times 500 bytes lands you in the low single-digit terabytes. That is very manageable. The hard part was never the storage size, it is serving the reads fast. One more quick number that scores points, bandwidth. If a redirect response is tiny, a few hundred bytes, then 4,000 reads a second is only on the order of a megabyte or 2 per second of outbound traffic. In other words, the redirect payload is small, the pressure is request rate and latency, not data volume. Notice how every estimate keeps pointing at the same conclusion. This is a read latency problem, so cache the reads and keep the redirect path short. That is the whole reason we estimate, not to be precise, but to let the numbers tell us where the design has to be strong. Step 3. Define the API. Keep it tiny. This system only needs 2 endpoints, and interviewers love when you resist overbuilding. The first is create. A post to /urls, with the long URL in the request body, and optionally a custom alias and an expiry. It returns the newly created short URL. That is your right path. The second is redirect. A get to /, then the short code, that is literally what the browser hits when someone clicks the link. The server looks up the code and responds with an HTTP redirect to the original long URL. That is your read path, and it is the one that runs 4,000 times a second. 2 endpoints. One writes a mapping, one reads it back. If you find yourself adding a dozen routes, you have wandered off the problem. 2 details worth naming to show polish. First, the create endpoint should be roughly idempotent. If the same user submits the same long URL twice, you can hand back the existing short code instead of minting a brand new one and wasting key space. Second, mention auth and rate limiting on create, so nobody can script a flood of junk links and burn through your codes. The redirect endpoint, by contrast, is public and unauthenticated. Anyone with the link can follow it. That is the entire point of the product. Naming which endpoint is protected and which is open is exactly the kind of small, sharp observation interviewers listen for. Step 4, the data model. Here is the insight that shapes your storage choice. This is fundamentally a key-value mapping. The short code is the key, the long URL is the value. Your core record is small, the short code, the original long URL, a created at timestamp, an owner or user ID, and an optional expiry. That is basically the whole schema. Now think about how it is accessed. Every single redirect is a point lookup. I have exactly one code, give me exactly one row. There are no joins, no range scans, no complex queries. That access pattern is the textbook case for a key-value store. It does one thing, look up a value by its key, and it does it blisteringly fast at huge scale. You can absolutely use a relational database here too, just put the primary index on the short code so lookups are order 1. But whichever you pick, say why, the workload is a simple, massive volume of key lookups, so you are choosing your storage to make that one operation as cheap as possible. And notice what we do not need. There are no relationships between links, no transactions spanning multiple rows, no complex reporting queries on the hot path. That absence is what justifies reaching for a key value or wide column store. You are trading rich query power you will never use for horizontal scalability and fast, simple lookups. When an interviewer hears you rule out features because the access pattern does not need them, that reads as real experience, not memorized trivia. Step 5 is the heart of the whole question: how do you actually generate the short code? Spend real time here, because this is the part that separates candidates. There are 3 classic approaches, and you should name the trade-offs of each. Approach 1, hash the long URL, run it through something like m.d.5, and take the first few characters as your code. It is simple and stateless. The problem is collisions. 2 different URLs, or just truncating a hash, can produce the same short code, and now you need extra logic to detect that clash and retry. It works, but you are managing collisions forever. Approach 2, and usually the cleanest, a counter encoded in base 62. Keep a global number that increments on every new link, 1, 2, 3, and encode that number in base 62, using the digits 0 through 9, lowercase a through z, and uppercase a through z. Because each number is unique, the codes are unique by construction, 0 collisions, ever. The catch: your codes are now sequential, which leaks how many links exist and is guessable, and the counter itself has to be coordinated across many servers, which is its own distributed systems problem. Approach 3, a key generation service. A separate service pre-generates a big pool of unique random base 62 keys ahead of time, offline, and hands them out on demand. Creating a link becomes just grabbing the next unused key, extremely fast, no collision checks on the hot path. And here is the number that reassures everyone: base 62 with just 7 characters gives you 62 to the 7th power, roughly 3.5 trillion possible codes. That is plenty of space to never run out with short links. My recommendation in the interview: the counter with base 62, or a key generation service. State that clearly. Step 6, draw the high-level design, connect the boxes so the interviewer sees the whole request flowing through your system. Start at the client, a browser or an app. It hits a load balancer, which spreads traffic across a pool of application servers. Keep those app servers stateless, so you can add or remove them freely and any server can handle any request. That is what gives you horizontal scale and high availability. Behind the app servers sit two things, a cache, like Redis, and the database, your key value store. And the cache is not decoration, given 4,000 reads a second, it is the whole game. Now trace both paths. The right path, a create request comes in, the app server generates a code, writes the code to u.r.l, mapping into the database, and returns the short link. The read path, which is the common one, a redirect comes in, the app server checks the cache first. Cache hit, return the long URL immediately, never touch the database. Cache miss, read from the database, populate the cache for next time, then redirect. Cache first, database second. That ordering is the point. Step 7 is a detail that catches people off guard, and dropping it signals depth. Which redirect do you send back, a 301 or a 302? They behave very differently, and there is a real trade-off. A 301 is a permanent redirect. The browser and any proxies in between cache it aggressively. So the next time that user clicks the link, they may jump straight to the destination without ever hitting your server again. That is great for load, fewer requests reach you. But it is terrible for analytics. If the click never reaches your server, you cannot count it. A 302 is a temporary redirect. Nothing gets cached, so every single click comes back through your server. That costs you more traffic, but now you can log every click, which is exactly what you want if analytics is a feature. So the answer is a trade-off, and saying it out loud is the whole point. Want maximum performance and do not care about per-click data? Use 301. Need analytics on every click? Use 302 and accept the extra load. There is no single right answer, there is the answer that matches the requirements you clarified back in Step 1. Step 8, Scaling. You already have the core system, now show how it survives real traffic. A few high-leverage moves. First, lean on the cache, hard. Link traffic follows a Pareto pattern, a small number of hot links get the overwhelming majority of clicks. Cache those hot codes in memory and most of your 4,000 reads a second never touch the database at all. Second, shard the database by the short code. Because every lookup is keyed on the code, you can partition the data across many machines by that key and each shard handles a slice, that scales storage and throughput cleanly. Third, put a CDN in front so redirects can be served closer to users geographically, cutting latency. Fourth, rate limit the create endpoint so nobody can flood you with junk links or exhaust your key space. Fifth, keep the read path fast by making analytics asynchronous. Do not log clicks inline while the user waits, drop each click event onto a queue like Kafka, and process it in the background. The redirect stays instant, the analytics catch up a moment later. And finally, use the expiry field to clean up, expired links get purged with a background job or a TTL, so old data does not pile up forever. So there is the entire answer, in one frame, the 8-step framework. 1. Clarify requirements, 2 functions, plus read heavy, high availability, low latency. 2. Estimate, round numbers, roughly 40 writes and 4,000 reads a second. 3. The API, just 2 endpoints, create and redirect. 4. The data model, a key value mapping, a point lookup by code. 5. Generate the code, hash, or a counter in base 62, or a key generation service. 6. The high-level design, client, load balancer, stateless app servers, cache, then database. 7. The redirect detail, 301 for performance, 302 for analytics. 8. Scale it, cache hot links, shard by code, a CDN, rate limits, async analytics, and expiry. Here is the real takeaway, this framework is not just for URL shorteners. Requirements, estimates, API, data model, core algorithm, high-level design, deep dive detail, then scaling. That same spine answers almost any system design question you will be handed. That is the URL shortener, answered the way that passes the interview. Clarify first, estimate with round numbers, keep the API tiny, treat it as a key-value lookup, nail the code generation, put a cache in front, know your 301 from your 302, and scale the read path. Do that, and you have not just answered one question, you have shown the interviewer a repeatable process they can trust on the next one. I put a full written system design interview guide at the link below, and if you want structured practice across many of these questions, the System Design Interview Prep Pack is in the description, $24, completely optional. Subscribe for more system design and developer interview breakdowns, and I will see you in the next one.